When we're looking at a rational function that's just given to us by a formula, so a rational function defined symbolically, we can figure out what the vertical and horizontal asymptotes are. The first thing that's helpful with vertical asymptotes is to remember what we said about the graph not crossing them, right? The graph never crosses a vertical asymptote. And what that means is that the vertical asymptote must occur at a value of x that is not in the domain, because the function is not defined there. So what we want to do to find where we may have vertical asymptotes is to look at the denominator and see where the denominator is 0. Those are the values that are not in the domain. Now, if you first cancel all your common factors so that what you're working with is a fully reduced function, then the zeros of the denominator are going to correspond exactly to the vertical asymptotes. So looking at this first function, f of x equals 2 over x minus 1, I'm going to take that denominator, see what makes the denominator equal to 0, and conclude that I must have a vertical asymptote at x equals 1. Coming over to Desmos.com just for a moment to look at this graph, I can see that it does look plausible if I plot x equals 1 on here and let that go away. I can see that that does look like where the vertical asymptote is on this graph. Now looking at the next rational function. My denominator is x squared plus 2 x squared plus 2, setting that equal to 0. Maybe I would try the square root method, but I would soon realize that these solutions are imaginary. If these aren't real numbers, then I really can't plot them in a Cartesian plane. I can't plot them anywhere on the number line. That's really the definition of a real number, is something that you can plot on the number line. And therefore, this has no vertical asymptotes. Coming over to Desmos.com again to look at this graph, it does seem plausible that this has no vertical asymptotes. I can zoom out just to make sure that I wasn't missing them, and I can see that as I zoom out further and further, this actually looks pretty close to a straight line. When I get closer to the center, I can see that it is not a straight line, but this doesn't have any vertical asymptotes. Now, I did mention that we need to cancel the common factors first. Looking back at these last two examples, it was pretty clear that there were no common factors we could have canceled. X squared plus 2 is prime. X minus 1 and 2 don't have any common factors, but this last one I may need to factor first. So x squared minus 1 is x plus 1 times x minus 1. And 4x squared minus 4x, I can just factor out that GCF of 4x, and that leaves me with x minus 1. Now, these two factors here of x minus 1 will cancel, and I really only have one factor that I would set equal to 0 for the sake of finding vertical asymptotes. Setting 4x equal to 0 and then dividing both sides by 4 gets me x equals 0. So I do expect to have a vertical asymptote at the y-intercept on this graph, and even though x minus 1 is not in the domain, it does not give me a vertical asymptote. Looking at this graph again in Desmos.com, we can see that in fact the y-axis does appear to be a vertical asymptote, and we can see that we don't have a vertical asymptote at x equals 1. What we can't really see is what's actually happening at x equals 1. What we have at x equals 1 is what we would call a hole. So bringing a snapshot of this graph over here, what I can do is draw an open circle right there. What that means is that for one instantaneous little point, that graph is undefined. But it's so small that we don't really see it in a computer-generated graph. We have to know that that's there, and that's what we call a hole. Right? So this graph has a hole. Just realized I was drawing that at x equals 2, but we had decided it was really at x equals 1 that we have that hole, right? That factor was common to both the numerator and denominator. So even though 1 isn't in the domain, it also isn't a vertical asymptote, and that's where it leaves us, is with a hole. So this has a vertical asymptote only at x equals 0, which is the same thing as saying a vertical asymptote at the y-axis. Finding horizontal asymptotes is a little bit more involved, and the simplest way of thinking about it is that it's similar to how we find polynomial end behavior. If you recall from polynomials, it was really the degree and the leading coefficient of the polynomial that determined what was going to happen for large, very large, positive or very large negative values of x. Well, the same thing is true with rational functions, but we really have a leading term on the top and a leading term on the bottom in a rational function. So looking at our first example here, 2 is the only term on the top, and x is the leading term on the bottom. The leading term is the one that has the highest power out of all the terms that are in that polynomial. So note this rule here, the leading terms dominate for large values of x, whether we're talking about large approaching positive infinity or large approaching negative infinity. So that applies to rational functions as well. And the end behavior of this, which is really what the horizontal asymptotes are if they exist, is end behavior. The end behavior is going to be the same as it would be for the function y equals 2 over x. So looking at some of these other examples, the leading term is 4x cubed. The leading term is x squared. Here, the end behavior is going to be the same as it is for the function y equals 4x cubed over x squared. And the nice thing about just looking at the leading terms is that then we can reduce it, right? Using the quotient rule here, I can see that this is equivalent to y equals 4x. And finally, looking at this case here, I have a leading term of x squared. I have a leading term of 4x squared. My end behavior for this function is going to be equivalent to the function y equals x squared over 4x squared. The x squareds in this case cancel, and I get just the number 1/4. So these three functions represent the three cases that can come up. We have the three cases listed above as maybe we have a horizontal asymptote at y equals 0. Maybe we have a horizontal asymptote at y equals some number that's not 0. And maybe we have no horizontal asymptote. All three of these things can and frequently do happen. The one that we can recognize most easily is the one that happens at a number that's not equal to 0. And that is the third one. If I end up with a number after reducing that expression, that is my horizontal asymptote. So I have a horizontal asymptote at y equals 1/4. Now, looking at the middle case next, y equals 4x is what I get describing the end behavior. Do you remember that when we looked at this graph, we zoomed way out and said, gosh, when you zoom out far enough, it looks like a straight line. When we zoom in a little closer, we can see that there's more going on. But when I zoom out really far, that looks like a straight line. Well, guess what? It actually looks like y equals 4x if you get out far enough. So this has the end behavior of a straight line. And a straight line does not have a horizontal asymptote. So this has no horizontal asymptote. Because the end behavior resembles a straight line. In particular, it resembles the line y equals 4x, which is a line that passes through the origin and has slope 4. It never approaches a constant value. The one that we already looked at that had end behavior like the line y equals 1/4, well, that had end behavior like a horizontal line. That's exactly what a horizontal asymptote is. Finally, we'll look at the first example, y equals 2/x. This is similar to our distance, rate, time example, right? If x increases as x gets bigger, two over x approaches 0. And so this one, because it still has an x in the denominator after we've reduced, this one has a horizontal asymptote at y equals 0. I'm going to start abbreviating this HA just to make sure that it still fits easily. So I can look at all three of these now and characterize them. And the characteristics that I describe right now are going to be true of all of these cases, right? The characteristic of my function f is that the degree in the denominator is bigger. When the degree of the denominator is greater, that means that the denominator grows faster than the numerator and the numbers get driven towards 0. The second one, the degree of the numerator is greater. When the degree of the numerator is greater, what happens is we get something that looks like a line or a polynomial in its end behavior, and you get no asymptotes at all. If the two degrees are the same, that's the only case where we get a horizontal asymptote that is a number other than 0. We can see why that's true. When the degrees are the same, that's the only situation in which the powers of x cancel out, leaving just a number. So we can think of it in terms of just looking at the leading terms and reducing. We can also think of it in terms of characterizing by the pattern we see in the degrees. In order to find this number 1/4, we really do need to take that ratio, right? We do need to set this up with the leading terms, see what cancels out, and see what number that remains. The other two can really be handled just by classifying it by where the degree is greater, in the numerator or in the denominator.